Hello everyone. So this is the eighth lecture in Unit 4, and in this lecture I'll discuss about the current source inverter fed induction motor drives for I by F control, you can say. So you can see that if we are having AC supply, so first we have to convert into DC with the help of controlled rectifier. So again we have to connect one large value inductance. Okay, so that we can convert this into equivalent current source. Okay, because inductor this will act as a current source. Okay, now again we are having current source inverter, something like this. So you can see that we are having six thyristors, and they are triggered as per their sequence, as per their numbers. Okay, and also we are having capacitors and diodes. Okay, for commutation purpose, because here we are having DC link, so self commutation is not possible, so we have to use auxiliary devices to commutate to turn off these thyristors at required time. Okay, so you can see that we are having three phase induction motor which is connected with this current source inverter, and based on the speed we have to send with tacho generator, then that reference speed is given to the firing control circuit, which generates firing pulses for these thyristors. Okay, so this will actually control the frequency, and for controlling this IT current we have to control these thyristors. Okay, similarly, if we are having DC supply here, so we have to use DC chopper to regulate this DC link current. Again, we have to use this inductor, okay, so that this ID should remain constant uh, for that interval. Okay, so this type of drives, you can see that a lot of devices we are using. So this type of drives, they are very costly, and they are recommended only for use in medium power and high power drives applications. But in next class you will see the cycloconverter fed induction motor drives. You will find that cycloconverters fed drives are preferred for current source inverter drives for high power applications. So you can see that the current applied to the stator windings, if we are if we are changing that, then speed torque characteristics will also get changed. Okay, so for three different currents you can see that the characteristic is getting changed, and for example we are having some load characteristics like this. So if you want to run at this speed, okay, we have to choose this current, and for this speed, for another speed we have to choose this characteristic. Okay, also you can see that the applied current or stator current and the rotor frequency, they are having a relationship like this. So they should control simultaneously, so that flux in the air gap should remain constant, because as I discussed in the last class, that there will be saturation if flux is increased, and the machine will run in saturation mode, and there will be more losses, and efficiency will gets down. Okay, also if we are running machine below rated flux, then the magnetic materials will remain unutilized, so under utilized machine will be there. So that is also not recommended, so we have to always keep flux constant, that is at the new point of the BH curve, and we have to regulate current and frequency in such a way that flux remains constant. So here you can see that if I take this IA current, this IP current, and this IC current, okay, so you can see that by proper switching the thyristors, we can have this stepped waveform like this. Okay, as you see that in V by F control, the stepped waveform you obtain for voltage. So here, this, since it is current source, by having a large inductance value, So we are getting stepped waveform for currents. Okay, so this current will have fundamental component, that is 50 hertz component, or whatever the time period corresponding with that, we will have fundamental component, then we will have harmonics components. Okay, so again, uh, in PWM again you will see that these low order harmonics will be eliminated. Okay, so this is a stepped wave operation of current source inverter fed induction motor drive. Similarly, you can have pulse width modulated inverter for induction motor drives that is fed from the current source inverter. Okay, now this is the closed loop control of CSI fed induction motor drives. So here you can see that we are having AC supply, then we are having fully controlled rectifier bridge, that is three phase bridge created with the help of thyristors. Okay, so that is controlled rectifier. We can control the output voltage and current from this controlled rectifier circuit. Then we are having a large value of inductor. Okay, so that we are getting a constant DC link current. Okay, so this DC link current for that particular value of alpha angles here, that will remain constant. Okay, and again we are having inverter. So inverter as it was shown here. So this inverter actually, okay, which is formed with the help of six controlled rectifier switches, six thyristor switches you can say that, and we are having capacitors and diode for commutation purpose. So with the help of this inverter we can change actually the frequency. Okay, so here we are changing only frequency with the help of this inverter. Now it is applied to the induction motor, which is changing its speed torque characteristic depending on the speed required, at what speed you want to run the motor. So the actual speed actually sensed with the tacho generator. Then reference speed, at what speed you want to run, you have to give it. Then the actual speed and the reference speed, they both are compared, and the error signal is fed to the speed controller and slip regulator, and it will produce a slip speed. Now the actual motor speed and slip speed, if you add both these two speeds, you will get synchronous speed. Okay, because synchronous speed is larger than motor speed, so you have to add slip speed in that, so that you can get the synchronous speed. Based on the synchronous speed, you can find out what will be the frequency that required to run this inverter. Okay, frequency means that time period actually. Okay, so from here to here, so one time period. So the timing actually you are controlling, that means frequency you are controlling from this inverter. Okay, so here only frequency is given. Now this slip speed is fed to the flux control block to produce the reference DC link current. Okay, now actual DC link current and this reference DC link current, they both are compared, that is fed to the current controller. Okay, which gives the signal to firing circuit control circuit, and it produces switching angle alpha for these controlled rectifier circuits. Okay, so here you can see that both frequency and the DC link current, they are controlled separately. Okay, so DC link current is controlled uh, from this fully controlled rectifier, and the frequency is controlled from this inverter. Okay. The details are given here, you can read these details. Now such a current source drive offers four quadrant operation with independent control of the DC link current and the output frequency. Okay, the motor current rise and fall are very fast. So fast rise and fall current will lead to high spikes in the voltage, because voltage is LDI or DT. Okay, if DI or DT is very fast or it is high, if di by dt is high, the voltage spikes will be more. Okay, so in these drives, the motors with less inductance value, okay, L di or dt. So if we reduce L value, so spikes will get reduced. So that's why the motor current rise and fall are very fast. Such a fast rise and fall of current through the leakage in the inductance of the motor produces large voltage spikes. Therefore, a motor with low inductance is used. Okay, and also even then voltage spikes are large. Well, the commutation capacitors also reduce the voltage spike. So capacitors have two functions. One is for the commutation purpose of the thyristors. Another is for reducing the voltage spikes. Okay, so this is the important point you should remember. Large value of capacitor is required to sufficiently reduce the voltage spikes. Due to large value of inductor and capacitor, the CSI drive is expensive and has more weight and volume. Okay, because inductor is heavy component, so volume and weight will be higher for these drives. Now there are comparison for CSI and VSI drives. So some important points I'm pointing here, but detail you can read in the next slide. So CSI is more reliable than VSI because there is no possibility of short circuiting here. In VSI, you have seen that if two switches in the same leg are turned on simultaneously due to commutation failures or some other reasons, then there will be direct short circuit in that leg and that switches will be damaged. So reliability of VSI is less in comparison to CSI. Okay. Because of large inductance in the DC link and large inverter capacitor, CSI drive has high cost, weight and volume, lower speed range and lower dynamic response. Okay. Whenever you are having inductances and capacitances in the circuit, then the dynamic response will become slow. The CSI drive is not suitable for multi-motor drives. If, for example, from one VSI, we want to run several motors, that is possible. Okay, so multi-motor drives is possible with the help of VSI, but that is not possible with the help of CSI drives. Okay, for each motor you have to use individual current source inverters. Okay, so in that case, the cost will further increase. So the detailed CSI and VSI based drives based system they are compared here. You can read these points easily. You will understand this. Okay, so in next class, that will be the last class for this unit 4. I will discuss cycloconverter fed induction motor drives. Okay, then I will also try to give you some solved examples on unit 4.